That's a good one. For those of you that have not seen the placement of low-density cellular concrete, it's playing a little video right now. It probably comes across a little choppy on you, but it'll give you a good sense of what it looks like when it's being placed. Low-density cellular concrete is very fluid when it's being placed and then cures as a solid. I am the global lightweight fill specialist for Eric's Industries, and have been working with lightweight fill materials since the early 90s. And cellular concrete sort of makes a very unique scenario because it is so lightweight. The definition of low density cellular concrete is defined by ACI 523 as a mixture of cement, water, and foam with no aggregate in it. So it's cement, water, and foam. And the key element is really that it's under 50 pounds per cubic foot, because the minute you go over 50 pounds per cubic foot, you're under ACI 229 and not under ACI 223. So with the mixture of cement, water, and foam under 50 pounds per cubic foot, it makes it an extremely lightweight fill material. And the air bubble that is in the mixture literally replaces the aggregate in the mixture. And it becomes extremely versatile at that point. When you look at the structure, the pore structure of the material, once it's cured, you will see the voids in it, and those are the leftover dissipated air bubble structures in the mixture. I think it's important to remember that low-density cellular concrete replaces traditionally compacted backfill. It is not designed to be the wearing surface or the driving surface of a project. So it literally replaces your sub-base material. It's extremely flowable and self-compacting. It's rapidly placed. There's two versions of low-density cellular concrete available, both a permeable and a non-permeable. That gives you the flexibility to address any hydrostatic issues if need be. Now, cellular concrete has got a tremendous advantage over traditionally compacted backfills. If you take, for example, 1,000 cubic yards of traditionally compacted backfill, it'll take about 100 truckloads to deliver that material, where cellular concrete will take about 45 truckloads. So you're drastically reducing the traffic on a project. You're eliminating all the compaction requirements. You don't have to do your traditional 6-inch to 8-inch lifts and compaction testing. You reduce your labor involved. You reduce your time involved in the compaction issues as well. So if you take a look at traditionally compacted backfill being at about 50 to 80 PSI at best, the strength requirements for low density cellular concrete will depend a little bit upon the density of the material, but generally falls between 70 to 225 PSI, which gives you an advantage over traditionally compacted backfill right off the bat with a low density cellular material, which is truly an engineered product. It's important to remember that as you go up in density, you go up in strength. My question is always, and I always ask this, when you go up in density, exceeding traditionally compacted backfill at 50 to 80 PSI, and now we're specifying 300, 500 PSI type material, why are we specifying that high of a density when we're replacing 50 to 80 PSI? The reason I mention that is because the minute you increase your densities, you're increasing your costs. So therefore, I always challenge it. Today, we don't have a lot of time to cover the various ASTM standards for low density cellular concrete. So we're going to skip over that. It is important, however, to remember that all QA, QC is always done out in the field, because that's ultimately where we pull the ingredients together to create low density cellular concrete. A key element I do want to point out is the importance of the water cement ratio, depending on what your requirements are. Always give a performance spec for low density cellular concrete and not a density, because when you just give a density spec, your water cement ratio can be played with and will affect your compressive strength. So work with your compressive strength when you do that. So I mentioned before that we have got both permeable and non-permeable cellular concrete available in the marketplace. So the first few that I'm going to cover from an applications perspective is the non-permeable, generally used as an annular fill or tunnel abandonment. And when you look at annular fills and things like that, you got to remember that you can pump tremendous distances because you're not pumping a heavy grout. You're now pumping low density cellular concrete. And low density cellular concrete is very fluid. So, and a tremendous amount of air in the material so that we can pump it much longer distances. The shrinkage of the material is less than 0.3%. So you're not going to have a shrinkage concern. I will advise you that because it's as fluid as it is, if there are any holes or voids that you're not aware of, it will get filled. So this is a typical type of project from an annular fill. It's deteriorating culvert relined with a corrugated metal culvert, and then the annular fill plugged in. And you can see the equipment involved as well. It's basically a ready-mix truck, a pumper, a foam generator, and then also by the fire hydrant, you can see the inline foam injector. So that is ultimately where the three ingredients come together. The longest distance that cellular concrete has been pumped on an annular fill is done in Hawaii. It was just over, just shy of 3 miles. It was a 13-foot tunnel lined with a 10-foot gravity sewer line, and they did the annular fill on that. They placed 28,000 cubic yards of material on this project with a 3- and 4-inch injection line, and the material was pumped just for 3 miles. In order to do that, though, there's a couple of things they had to do. One, they used a retarder on the material. They chilled the water from 70 degrees down to 50 degrees, and they maintained their lift heights as well in order to control the curing process of low-density cellular concrete. A little bit closer to home, Baton Rouge, there was an annular fill project that was done on some deteriorating metal culverts. They were relined. They were 60 inches, and they were relined with a 54-inch snap-tie pipe, and then filled with the annular fill on that. And then, you know, you go to void fill or utility abandonment projects. Again, cellular concrete is extremely fluid when it's being placed. So it will find every nook and cranny. And it's a great example of what's shown on the screen right now of self-leveling as well. Most recently, there was the abandonment of the Battery Street Tunnel in Seattle with the rebuilding of the new structures there. These prior projects, most of them are non-permeable. On the permeable side, permeability is extremely 10 to the -1, 10 to the -2, somewhere in that area, depending on the density being placed. And the difference between permeable and non-permeable is within the chemistry of the air bubble. Where with the non-permeable, we want the bubbles to maintain its structure, where with a permeable material, we want those bubbles to coalesce or unite to create open cell technology. Generally, permeable cellular concrete is placed between 25 to 35 pounds per cubic foot, because that is where we see the best permeability, the best infiltration of the material. And it is extremely permeable. And like I said before, it's probably 10 to the minus 1, 10 to the minus 2. On a project that was done in Bronson, Missouri, the Missouri DOT wanted to have a demonstration of the permeability. So they asked the contractor to dig a 4-foot deep trench and fill it up with permeable cellular concrete. And the video demonstrates the permeability of the material that day. It was placed one afternoon. The next morning, the Missouri DOT folks came out. The void structure with permeable cellular concrete is pretty extreme. And we will never fill 100% of those voids. Permeable cellular concrete cannot be placed to displace water. Neither can the non-permeable material. However, with the permeability of the permeable cellular concrete, you can allow water to infiltrate into the material and counteract any buoyancy concerns that you might encounter. So that brings us up to the opportunities for soft soil remediation, and I'll show you some examples of some projects that were done. I think it's also important to remember the elimination of lateral loads upon structures at the same time. In Florida, there was a project that was done against the placement of some material against some sheet pile walls that were driven in, and to reduce the load on the soft soil remediation, and to stay within potential settlement concerns. This was 2,800 cubic yards of material that was placed in 2.5 evenings. They did all the work at night so that they kept the ready-mix trucks off of the main road during the daytime hours. A lot of questions always comes up is on the loading factors. And, commuter rail and heavy rail is always a good example for loadings on soft soil remediation and lightening up the load on those compressible soils. This was a project that was done in Secaucus, New Jersey, with some track widening projects. And you can see where the low density cellular concrete was placed against the 5-foot segmental wall there. And I'll show you some close-up pictures on that in a little bit. For another project for soft soil remediation was in New Orleans on the new lightning bolt building on the airport there. And they excavated out 4 feet of I guess I would call it muck, which is compressible organic peats that goes on forever. And to lighten up the load there and maintain the settlement concerns, that they took out 4 feet of the original peat and then placed the permeable cellular concrete. Today, this project acts like a great big sponge. As the water table rises, it infiltrates into the permeable cellular concrete, and as the water table drops, it's released again. So you're literally counteracting any buoyancy concerns. Another area that needs to give some consideration with the non-permeable material would be the incorporation in elevating or increasing the elevation of levees with the non-permeable material, where you can increase the elevations, make sure you have the appropriate amount of overburden upon the low density cellular concrete, and increase that elevation. From a retaining structure perspective, a couple of things to remember on that. The material is awfully fluid when it's being placed. But once the material has cured against that vertical fascia wall and you have replaced the sliding wedge of the soil, you will end up having a 0 lateral load factor once it's cured. The only time you're going to have a lateral load is during the liquid phase of the cellular concrete. Going back to the Amtrak project that I showed you a little bit ago. Just some details on the vertical fascia wall and the precast walls, 5-foot segmental walls there. And you can see where the geomembrane was been placed against the wall to prevent any seepage from occurring as well. And again, in this case, they have totally replaced the sliding wedge of the soil to create that zero lateral load. With that, you'll obviously change your footer as well, because you've reduced or eliminated those loads. A lot of questions always comes up with strapping configurations. You can put a strap within the lift or in between lifts. It makes no difference. There are some engineering firms that have a preference of one over the other. For example, Rico likes to have it within the lift. Others don't care. From an internal angle of friction, you can pretty well figure that the internal angle of friction on low density cellular concrete conservatively is about 35, 40 degrees. That's actually very conservative. Liberally, I would probably go 60 to 70 degrees, because it all makes a difference of whether you're designing a soil wall or a concrete wall. One of the highest vertical fascia walls that I have seen is in Bellingham, Washington, where both these abutments are permeable cellular concrete, exceed over 50 feet in height, and then they place shotcrete as the fascia walls over those. So it's a great example of the elimination of lateral loads. A lot of times I get asked the question, well, how high can I go with a vertical fascia wall? There really is no height limitation, because your limitation is a height-width relationship to wind overtopping, which will be a true height limitation. A couple more projects here from underground utility conduit perspectives as well. If you've got underground utilities, you can place them much closer together than you would traditionally do with compacted fill, because you can get right into the hunch of the project, and no compacting requirements are involved at that point. Cellular concrete is extremely excavatable and very versatile should you have the utility that has to be placed after the fact. So we can excavate it out very well. To get a nice clean cut does take a concrete saw before you do a lot of excavating out of it. So that sort of brings me to my brief presentation here. You know, I promised the organizers to keep it down because of the other speakers involved. Cellular concrete's available in a broad range of densities, very economical, versatile, it's rapidly placed. You can generally place low density concrete anywhere from a yard at a time to several hundred yards per hour. So it is extremely fast. So, and I don't know if we have time for questions or not, but I would like to thank everybody for participating.
Thank you very much, Nico. I appreciate you.